Right. Good evening, everyone. We'll be getting started in just about a minute. All right, let's begin. So, once again, thanks for coming this evening. We're going to be diving into a little more depth on the topic of steganography, which we had started looking at last Monday at the Intersect talk. We went over some of the basics, some different techniques, mostly how to recognize it and what it is. Today, we'll be having a closer look at how to actually apply it in practice. So, just a quick recap. So, cryptography and steganography might sound pretty similar, but they are different ideas. Cryptography is going to take some secret and transform it so that it can no longer be understood. So, for example, the GUV EBG13. Well, it means something. I don't know what it means, but we'll probably get to decoding that next week. But steganography is different. So it's kind of hiding something in plain sight, or hiding the secret in something that doesn't look like it's suspicious at all. So, for example, if I put my secret data into a cat picture and a casual inspection wouldn't reveal that there was a secret in there, that's steganography. So, when a malware botnet is controlled by cryptic comments posted to someone's Instagram page, that's steganography. When Digimarc decides that they're going to cover every surface in the universe with barcodes, that is steganography and terrible. And when you learn the truth about the weather machine to uncover the secret conspiracy underpinning all of existence, so that's kind of steganography, you think about it. So, again, all these things kind of the underpinning, the core element here is that you don't actually know there's a secret there. All you see there's something, but that something looks innocuous, whether it's an Instagram comment or a thing of coffee or a billboard. And last Monday we talked about some different flavors of this, concatenating files and using weird text formatting to hide things, using weird text patterns like those cryptic comments, and then a lot of bit manipulation, which we'll be delving into a lot more today, as well as other, such as image, bit plane, complexity, segmentation, steganography. I didn't understand it. And we're not going to deal with it. So, as I promised, we'll be looking at how to actually perform steganography and how to, actually use and practice both encoding and decoding. And because copying code from a slideshow is probably the worst experience possible, we're going to be giving y'all both the code and the kind of demo files that we're using here. So, as a refresher, and for those who didn't catch Monday, when I say bit twiddling, I'm talking about taking a piece of data and slightly modifying it, so tweaking just one bit at a time to encode something. So, for example, these two images are actually different. Like this red is slightly darker than this red. Now, obviously, that's not really visible, and that's actually the point. So, by manipulating just a little bit of data, we can just kind of imperceptibly change it and encode something. And just to illustrate, this is the most significant bit changing. You see this red got way less intense. It's more of a weird kind of orangey color. So no matter what we're really dealing with, the process is pretty straightforward. We get some data, the cover, so for example, a cat picture or a piece of music, and we get our secret, which is what we want to actually hide. The secret is generally much smaller than the cover, because again, if we're only getting like one bit at a time here, we better have a lot of pixels. So we then take the secret and store it in the cover, and then we export the resulting data. So for images, we're going to do this in Python. We're going to use the pillow library to import the image as a giant array of numbers, go through that array and tweak it, and then export the image back out. And if we're doing audio, it's the same deal. We import a WAV file as a gigantic list of numbers, we tweak it, and we export it. So you can grab the demo archive like so. Let me actually clean this all up. I was making sure everything was working right. We'll just knock you all out. Okay. So you can just download them from the tools website, which if you go to it, you'll see links to both the slides and to the demo materials. But you can also just directly download them like this. And that should bring in, Stegatools, taro.gz. And I'll just open that up. And we'll go in. So this is all set up, ready to go, with one caveat. If you try to run these scripts right now, you're probably going to get some errors because we don't have any of this stuff installed yet. Fortunately, that's pretty easy. So there's just 3 steps you need if you're following along at home to be able to execute all the stuff we're doing today. You're going to set up a virtual environment, activate it, and install everything. You could also just install everything directly if you wanted to, but I like to keep things a little tidy on my machine. I know some other people are not nearly as neat. And if you miss any steps, you can just pop open the slides. They'll be on the tools website. They should be there already, actually. So I'm just going to install our stuff, and that'll go on in the background. So the first thing we're going to look at is this bits.py script. So as I suggested, the process is really quite simple, but you might as well just have another look at it here. So when we're encoding, we're going to take our secret, like let's say letter A here, and we're going to take one bit at a time. And each of those bits will just get stuffed into one piece of data. So in this case, the image is just a gigantic list of red, green, and blue. So it's like, maybe it's 255, 0, 255, that would be purple, or, any other color you want. And all we're going to do is just tweak that lowest bit. And to decode, we just do the opposite. We read through each of these pixels, and we go through each of its colors, and we just take the lowest bit and read it right out, and that'll build up our secret data. So this should be finished. Yep, get a nice warning there, but clear that. So if you run Python bits.py here, you'll see it set up already with some hints. So say I'm going to encode something into a picture. I'll do encode image. And I want to do it with, let's say, I think the RPISec logo sounds good. So we're going to write RPISec, and we're going to write that out to encoded.png. Now, we have a look at this file here. This looks pretty normal. I think that's a pretty classic PNG right there, to say so myself. But we can then read the data right back out. So if I say, use bits.py decode image, and we're going to give it the encoded thing, and you'll notice that it wants a length, because there's one problem with this scheme. It doesn't know how much data there is. It's going to keep reading and reading, and if we ask for a lot of data, that's going to be a train wreck. As you can see, it's just Y forever. So just as it screams Y, I will ask Y and not do that. So we just give it a length and it'll stop there. So there we go, RPISec. It's pretty simple. Let's have a peek at that thing. We have Visual Studio Code installed for you, so you can just open up any file you want with that. So the actual process is pretty simple, and we're not going to do a line-by-line code analysis here, because again, I think that would be pretty miserable. But basically, if you want to have a close look, you can just pop this open and read through it. The process is pretty straightforward. We just kind of figure out which bit we want, we poke that bit or we pull that bit, and that's all we do. And so there's another glorious image in there of our beloved cis man, who will be making many appearances throughout this presentation. Spoilers. Here we can see I've encoded the word RPA into it, and you see how it's all weird and assorted? It's because I took it in Photoshop and it's kind of squished all the colors so you could actually see this stuff. And you can see up there we got these weird colors. That's our text. And our terrifying visage of the computer man. I don't know what a JPEG is. And as I said, this thing doesn't know how long the secret is. Maybe a smart thing to do would be to write that first. Maybe a fun exercise for the viewer later on. But anyway, so yeah, we just give it a length and it stops 0. Pretty straightforward. Now, as I said, doing this is pretty consistent no matter what you're working with. Images, audio, video, text. We just need a big lit pile of data and a way to manipulate it. So when we're dealing with audio, we just have a long sequence of samples. It just, that's all a WAV file is. And again, we just tweak that lowest bit or tweak that second bit or whatever bit we want. And we read the data back out the same way. Just read that bit, stick them all together, you get a string. So you can do the exact same thing to manipulate an audio file. I think I have an example here. So here, this is a visualization of the wave. And you can see I've hidden this little flag in there. So the normal file just kind of looks like this. So it's mostly silent with a few tweaks. But when we've actually stegoed this data in, what we've done is change the lowest bit up or down. So now, instead of 0, 0, 0, 0, 0, it's like 0, 1, 0, 1, 0, 0, and so forth. It's kind of sus. Out it goes. So yeah. This is a pretty bare-bones script overall. It doesn't let you pick which bit to set. It doesn't let you do video. There's a lot of stuff you could do to extend this. And I think it's actually pretty straightforward to do so. There's a lot of nice Python libraries out there for this kind of stuff. Images, video, audio, text, I hope, and so forth. So yeah. Let's zip around here a little, close that up. So that's the first kind of thing we looked at. And that was just straightforward sticking data into the least significant bits. Really common stego technique. But let's say I want to put a whole image in there. And it's kind of annoying to have to go reconstruct it carefully by, reading individual bits out of pixels. I should do this all at once. And if you think about it, we could just kind of copy some of the stegoed image into the cover data and just stick them together. So, to that end, I've decided I'm going to glue together this great picture of us winning great things at DEF CON with Sysman. Now, when I combine them, you'll probably notice that this looks like a normal image. And that's the point. Well, this is Steganography. It's great. So there is actually, if this image wasn't so noisy, you'd be able to see something. And what that something is terrifying. So all we've done here is take the least significant bit from each pixel of Sysman and copied them over to the cover image. And I used CyberChef to visualize this. So all I did with it, I asked it to show me the least significant bit of the red channel. And it'll pop that out for me. So you get this beautiful two-tone image. And as I said, that image is kind of noisy. It's got a lot of, there's a lot of stuff going on here. There's people, there's textures, there's all the kind of stuff. On the other hand, if I use an image that's pretty bland, like this background, it's got a lot of, blank space to it. And it's actually kind of hard to see. I think the compression kills it. But if we use more bits, you start to see it. There's our favorite computer mascot just vibing in the background. So it is actually hidden in here. But one problem with steganography is that it often takes advantage of things that image compression and audio compression just deliberately gets rid of because you can't see it. So JPEGs and MP3s are a lot more annoying to stego than something like a PNG or a WAV. So that's something to keep in consideration, both when you're producing steganographically encoded data and when you're trying to spot it. And naturally, if I copy every single bit, you just get the original image. So there you go. And if you want to do that yourself, you just want to check out, there's a script called overlay, which will do that for you. And it actually lets you pick how many bits you want. So let's say I'm going to combine the RPISec logo with us at DEF CON, maybe. And we're going to say mix.png, and let's use 4 bits. See what we got. So, kind of not too surprising here. And we wind up with something that looks a little bit like both. And all we're doing here is we're taking the original image and we're crushing it down to like 1 or 2 or 3 or however many bits. And then the other image, we're just hollowing out those lowest bits, and then we glue them together. Now, it's kind of fun to do that with images, but that's kind of obvious. It's straightforward, it's boring. I want to do something weirder. So I want to take an image and a piece of audio and combine them. Now, normally if you tried to open both those in Photoshop, you get an error, because audio is not an image, unsurprisingly. But we can interpret it as an image. So we talked about spec way back in that toolbox talk at the start of the academic year. And let's have a look at this this snippet of the classic In the Hall of the Mountain King song. And spec will just let us have a look at that. So this is a spectrogram. It's got time on the x-axis and frequency on the y-axis with brightness indicating intensity. So this kind of shows you, where there's high-pitch stuff, where there's low-pitch stuff, all that good stuff. And here's that image again. So you're probably used to seeing audio as time versus intensity. And if I go back a little bit, back to here, like this is time versus intensity. And that's pretty straightforward. But this is a little weirder because we're dealing with frequency information. So to get the spectrogram, we can do that in Python using a Fourier transform. I probably mispronounced that. It's French. Now, the fast transform, FFT, will let us, very quickly, as the name implies, compute this. And this will let us do all sorts of useful stuff. It lets us, identify songs by looking at their kind of tonal makeup. We can spot noise, we can spot all this kind of stuff. But we don't want to do that lame, normal stuff. We're going to treat it like an image. So there's a third script in here, spectrogram.py, which will let us smash together some audio with some images. And you think about it, so the Fourier transform gave us this kind of two-dimensional thing. And it's every pixel, so to say, every intersection of like time and frequency, we have a little spot, and we can change that. And of course, an image looks a lot like an image, because it is one. So that means that we got 2 of the same thing here. So let's just add In the Hall of the Mountain King with Sysman. What do we get? Absolute terror. That's what we get. Let's give that a try. So I'm just going to say Python spectrogram, see what it wants. So we're going to give it a WAV file. We're going to give it an image. Actually, let's do a different one. Let's do DEF CON. And then we just give an output file, mix.wav. I need to make that, print that out. And if we now pop this open in spec, full screen it, there we go. So you see it's gotten very kind of blobby looking, and that's because this isn't really a nice square pixeled image. There's there's like thousands of time kind of buckets on this axis and only something like 64 frequency buckets. So you see we have these long smeared out kind of blobs of color. And so yeah, it's not exactly perfect. I was gonna put a Rickroll QR code in this, but I couldn't get it to render properly, so I'm very sorry. So we get some really weird sounding audio. I don't have it set up right now to play this, but if you do that yourself and give it a listen, it's going to be this weird wavy kind. You get all these sounds rising and falling because again, audio doesn't look like this normally. This is not correct. This isn't what music sounds like. It's what absolute terror sounds like. And just as a pop cultural warning, this has been used off and on quite a few times for kind of this fun little Easter egg, like Nine Inch Nails in their song "My Violent Heart" kind of threw in this weird-looking hand in the spectrogram. And I've seen this in a lot of ARGs, a lot of that kind of stuff. It's fun and it's surprisingly easy. So it's a pretty cool effect. And then here's just for some vanity's sake, the RPSec logo slapped onto a piece of music, So yeah, as I suggest, and that's a typo, you can just run it with Spectrogram. So just give it a wave, give it an image, get yourself a modified file. So this is all cool and good. We've come up with these really weird things. We're putting text into images. We're putting images into images. We're putting images into audio files. And you can go further from there. You can stick data into videos because a video is just a bunch of images and some audio too. And text is just a sequence of bytes. Really, when you think about it in this abstract model, this kind of bit twiddling model, you can do a lot of stuff. You just need to come up with a way to load it and save it. Now, so that's all cool, but we got a big problem here. So this is kind of what you might call security by obscurity, which I never liked the term much myself, but it is true that the way steganography works is you hide the fact the secret exists rather than making the secret impossible to read. So if your adversary knows to look for it, so for example, if you Google free steganography library and you just use the defaults, it's going to be extremely obvious. Like a lot of people have heard of hiding data in an image by messing with the least significant bits. So you kind of have to rely on your adversary not knowing about the existence of the system you're using to, use it. And that's not so good. So that's where encryption comes in. So encryption actually lets us, with keeping secret only a little secret key, we can encrypt a ton of data and it's completely unreadable. And, unless people find bugs in it, the sun will burn out before we can actually break it by brute force, which is probably a little more secure than whatever this is, So we need encryption, which we're going to learn about next week. So if you come back next Monday, we're going to be talking about the foundations of cryptography, like the classical stuff, the Caesar cipher, I guess the Pigpen stuff, all that kind of old fun stuff. And next Friday, we'll be talking about more modern cryptography, the stuff that actually kind of gets used to keep your data safe. Not the really modern stuff. That's the week afterward. Don't get too excited. But yes, so that's going to about wrap things up for today. I might run through some more kind of just live stuff here, but that's the end of the slides. So again, if you'd like to keep in touch with us, you should pop over to the Slack channel. And I'll just show you how to get there real quick. You go to tools.rps.ec. You'll find our tools website. And over here, you see we got today's slides, so we can open them up in here. It's a little meta. And we also got our resources. Don't need that. But we also got links to our Slack and our mailing list, as well as Fair Game, our kind of intro newbie-friendly CTF, which, there it goes. Thank you, Firefox. So check all those things out. Definitely the Slack, though. We'd love to see everyone who's been watching come in, say hi, learn some more good cybersecurity goodness. So yeah, that about wraps it up for today. So, barring any terrible ideas here, wait to see if we got any questions in the chat. We'll wrap things up. I'm going to try to shove an image into a WAV file. It's going to be great. Let's see. Okay. Let's see. Can we do this? Code and image. That's the wrong one. You see, I'm very good at this. Oh yeah. See if that worked. That is not the right kind of file. That doesn't look so good. I don't think it liked that. But yeah, if you got any questions, then we'll be wrapping the stream up. So thanks again for coming by, and we hope to see all of y'all in the Slack.